Starting with this video, we are going to study Galois extensions, and hopefully in the upcoming videos we are going to characterize Galois extensions in terms of the so-called properties of normality and separability. So here are some details. We start with a field extension. Its Galois group is defined to be the set of all F automorphisms of the extension field, the over field E. And that can be checked to be a subgroup of the automorphism group of E easily. And on the other hand, if you start with a subgroup H, say, of the automorphism group of E, then this defines the fixed field of H. That is the set of all elements of E fixed by all elements of H. Okay. Here are some basic properties that we will go over one by one, but at this point I would like to urge the viewer to pause the video and go over these properties on their own. The first one says, if you have a succession of field extensions like this, then the bigger the subfield is, the smaller its Galois group is. Similarly, for two subgroups of the automorphism group of E, the bigger the subgroup, the smaller its fixed subfield. If what you start out with is the fixed field of some subgroup itself, then applying successively first the Galois operator and the fixed operator, you retain the first object you started with. Similar thing happens with the Galois group of an extension or a subfield. Now, every field is contained in the fixed field of its Galois group, and every subgroup of the automorphism group of E is contained in the Galois group of its fixed field. If in these inclusions you have equality, then we say, for example, if here in the first one, if you have an equality instead of just an inclusion, then we say F is closed in E, or F is a closed subfield of E. And in the second one, if equality occurs, then we say H is a closed subgroup of the automorphism group of E. Now, here's what a Galois extension is. It's a finite degree extension where F, the ground field, is a closed subfield of E. So our aim is to characterize when a finite dimensional extension is Galois. Here are some basics. So if you have an extension like this and a non-zero polynomial over the ground field F, or the base field F, and if omega denotes the roots of F in E, and G denotes the Galois group of the extension, then we do know by a previous observation that every element of G induces a permutation of omega, and thus in return a group action, namely an action of G on omega like this, defined by this rule. And that action induces a homomorphism, like so, and that homomorphism is kernel equal to the set of all elements of G, which, when restricted to the extension of F in E by omega, coincides with the automorphism of that extension. So in particular, if your E is equal to this extension, then phi will be a one-to-one map, making, yielding a group embedding. Well, let's assume furthermore that E is now a splitting field of some polynomial in Fx, not necessarily F, and F is irreducible over F. Take any two roots of F, say alpha and beta. any two roots in E. Then a prior result tells us that there's an F isomorphism between these extensions, say omega, not omega, I'm sorry, phi, that takes alpha to beta. Now, we took E to be, initially to be a splitting field for a polynomial, for some polynomial over F. Now, since each of these subfields contains F, E is then a splitting field over each of these subfields for the same polynomial. But at this point, we invoke one of the results that can be obtained slightly more generally from one of the examples left in a video. So phi can be extended to some automorphism phi bar of E, and this argument tells us that under the hypotheses 1 and 2, namely these, the action of G on omega becomes a transitive one, namely it has a single orbit. So this concludes the video number 6. I hope to see you in video number 7. Thanks for listening.